Hello, everyone. Welcome to today's UK-SOSS talk. Today, we're pleased to have Dr. Hugh Hudson from University of Glasgow and UC Berkeley as our speaker. His talk will be on Carrington events. So yeah, without further ado, let's get started. Hugh, please.
Okay, thank you, Jaja, and thank you, everybody. I'd like to especially say that this is a very nice opportunity for me to introduce myself to the British community. I've sort of parachuted into Glasgow about 10 or 15 years ago, and I'm an American, as you can tell. So and I found a very warm reception here, and I'm happily doing as much as I can do in retirement. And one of the topics here that's of great interest is the Carrington events. And at Lydia Van Driel's request, I've actually written a review of this subject for annual reviews. And I've also shared an office over the last year, prior to the pandemic at least, with Ed Cliver, who's a great expert on this topic and who is in the process of writing a major article on extreme solar events for the living reviews in solar physics. So what I want to talk about is the Carrington event and what is it, and what is any event actually, and to talk a little bit about the novel tools we have now to think about extreme events, which are two. There are tree rings and there are stellar flares that kind of help to inform us about the possibility of really extreme events on the sun, such as the Carrington event. And of course, the question we're all interested in is, will an extreme event smite us at some point, destroying all of our communication satellites and power grids and causing trillions of dollars worth of damage? So this is all pretty concretely interesting, right? And let's see, can I advance? Ooh, there it goes. Okay, so who was Carrington to start with? First of all, he was not Lord Carrington. There was a Lord Carrington in the 19th century. No, our Carrington, Richard Carrington, was just an astronomer born in 1826, and as the son of a brewer, a prosperous brewer. He had independent wealth and could make his own observatory and do wonderful observational work. Unfortunately, he left no picture that we know of himself behind, but you can see this picture that Ed Cliver took at the in Burlington House of the library stacks there, and you can see the monthly notices going along before Carrington, and then during Carrington, the monthly notices got bigger because he was creating so much data. He insisted on having a large format, and then later on it reverted to the usual form. So Sean Prosser from the RAS has made available this nice picture that this is actually a sketch, one of his sketches, which he made very precisely on a projected image of about this diameter, probably, on a screen with a pale distemper of straw, as he wrote in his paper on the solar flare of 1859. And so you can see the color here, pale distemper of straw. So he was his activity was to make very precise measurements of the positions and the sizes and shapes and configurations of sunspots, which were used for several purposes, measuring solar rotation, for example, and generally studying the behavior of sunspots, which remains, of course, a very interesting subject. And while he was doing this very precise geometrical work involving these sketches, in 1859, September the 1st, he noticed in this huge group up here, the sunspot group, the flare happened. And so this was the beginning of the research, a whole amount, the research area that we follow now in great numbers and with some success, but not complete. Right, so this is the spot group close up, and you can see, I think I have an even bigger version of it. So you can see the A and B places here. These are the two ribbons we would now identify it of this flare. And so he sketched this location, and then he went off to get his assistant to come back and confirm that he was seeing something really weird on the sun. Assistant came back, and Carrington writes in his article He was mortified that the thing had gotten a lot fainter, and in 5 minutes, and here it is 5 minutes later at C and D. So from A and B, pretty bright, as bright as the quiet sun itself again, and then fainter down here at C and D, and lasting for 5 minutes. So that's not the only remarkable thing. The most, what I think is even more remarkable is that about a year ahead of that time, there had been a new high technology recording magnetograph installed at Kew Gardens, made by a man named Welsh, and written up by Balfour Stewart in a paper in 1860, in which they also observed this flare. They observed the flare in the Earth's magnetic field in 2 or 3 ways, right? In the first way, this is a very complicated set of plots, so I'll describe them to you. There are 3 coordinates of the Earth's magnetic field, which they are called west declination, horizontal force, and vertical force. And these are plots that go for the whole day, August 30, 31, and September 1. So 3 consecutive days in each of these coordinates. And at this time, at the time of the flare, within a few seconds, according to Carrington, who was making very precise time measurements, of course, and it was in his nature, there was this thing that appeared here, which became called a crotchet. And there's a debate about how you pronounce this. Ed thinks it's crochet, I think it's crotchet. But in any case, it's been replaced by a 3-letter acronym. Now it's called the SFE. I think that's unfortunate because either crotchet or crochet is a lot more demonstrative. In any case, this crotchet happened. That lasted for tens of minutes. You can see 11 hours, 1100 and 1200 Greenwich time on September 1st. And then on September 2nd, there was this sudden commencement, which is called a sudden commencement in the geomagnetic storm, right? And after that, this beautiful device, the recording magnetograph, went off scale, and the storm happened. But it was measured elsewhere to have a very large DST index, one of the largest. DST is measured in nanoteslas. The unit here is gammas. I challenge I challenge all of you to tell me what a gamma is. Excuse me. Okay, so this was clearly the beginning of multi-messenger astronomy in terms of astronomical transient events, because you were seeing this flare not just by the light that the flare emitted, but also by its effects through high energy radiation, but also particles and gas striking the Earth's magnetosphere. And this was sort of the beginning of space weather. So, and I have to say, as an American, I'm rather proud because although that subject was quickly dropped in the UK under the domineering influence of Lord Kelvin, who had dismissed any possibility that the sun could ever affect the Earth's magnetic field, still it was followed up in great detail by an American astronomer named Loomis, and this was summarized in several papers that Peggy Shea wrote, described in 2006. So if you're interested in the history of space weather, I would recommend looking at this paper and seeing what the Loomis collected in terms of the global knowledge about the disturbances that this flare caused. And here's the instrument. I thought I would show this, not that I understand it fully, because it's like a steampunk kind of Hollywood thing. This is really a very high-tech Victorian instrument, which recorded the Earth's magnetic field without the benefit of electricity, right? This is, and of course not computers, right? This is with these magnetometers that are suspended mirrors, and they're being illuminated by gas flames, and there's the gas piping that goes down there. And these light beams reflected off of these mirrors go into this box where there's a rotating drum driven by clockwork. And here are the clockwork weights. There's a pendulum swinging back and forth. So in here, there are 3 rotating drums, and these light beams are leaving imprints upon photosensitive surface, a paper wrapped around the drums. So these photographic traces are what's been transcribed here by probably Balfour himself, but republished in many places. So anyway, it's remarkable that they could do this. Prior to this time, with this recording magnetograph, it required people to read the geomagnetic records every 10 or 15 minutes and write that down in pencil and paper somewhere. But here you got a full record with very high precision. You can see the fluctuations here are on the order of a few gamma. A gamma is 10 to the minus 5 Gauss in modern units. And so this is quite a precise measurement. Okay, but not as precise as modern ones. So a modern crotchet, there's an example of September 7, 2011, is seen so beautifully here. And this is the magnetometer trace from Kapioka, this gray line here. You can see all kinds of ripples at parts per million. This is very sensitive and precise measurement. So the flare happens and whoop, it goes up and then it comes down again. And so then at the same time, almost, there is the GOES soft X-ray signal. And there is helium-2, I think, sorry, that's the GOES is the green and helium-2 is from Eve is the blue. Up here that's blown up so you can see it in more detail. In comparison with those X-ray and EUV signatures, what is more important for the crotchet, it turns out, is Lyman alpha. And so Lyman alpha is the solid histogram here. And I think this figure came from Brian Milligan's paper in 2020, and it may have been made by Laura Hayes. To give proper credit, I would have to track that down. In any case, this is these crotchets are a perfectly good way to see X-rays coming from the sun or Lyman alpha. And back, of course, in Carrington's day, X-rays had not been invented yet. The ionosphere was not known to exist. Ions probably were also not known. So all this was in the far future. Röntgen was not even born, and yet here was the flare. And now we understand the explanation of these ionospheric effects in terms of currents that are being driven by this a large-scale electric field that is created by the solar wind flowing past the magnetosphere. This electric field drives currents that flow in the ionosphere, and these currents are greatly enhanced when the ionization increases, and the ionization results from this hard radiation from the sun. Right, so how important was this? How big a deal was this? Certainly, people have gone back and looked in different ways at how big this event was, and it was near the top of all the league tables that you can imagine in terms of the crotchet amplitude, the magnetic storm magnitude, the extent of the aurora in latitude, the speed at which the disturbance, the CME disturbance got from the sun to the earth. These are all, Carrington's event was one of the top ones in all of these categories. And so that is why it is now taken kind of as a paradigm for the super flare. But we should be careful about calling it a super flare because other flares have not been so different. This was just at the top of the league table, near the top, but not the very top, perhaps in some categories. And so how much energy was involved? So Carrington could have done this calculation, right? If you take the flare intensity, doubling or trebling the quiet photosphere, take the area that he sketched out, maybe 0.01% of the area of the disk, the duration, 5 minutes, the time for him to call his assistant to come confirm. If you just put that together, it gives you a few times 10 to the 32 ergs. And then if you just guess that the CME was a typical huge CME mass of 10 to the 16th grams and calculate 1/2 NV squared, because you know how long it took to get to the Earth, you get, it turns out, exactly the same number. So the total event energy was a few times 10 to the 32 ergs. And as I say, Carrington could have made this estimate, but he wouldn't have done it in ergs. because they weren't invented until 1873. So he would have done it in British thermal units, maybe, or who knows, foot pounds. Okay, so here's the league table. Here's the statistics, the power law. I think many of you are familiar with this power law, but there is a distribution function for flare magnitudes, and often these flare magnitudes are converted to energy. So in that case, the y-axis would be ergs, and you would have 10 to the 32 out here. But this distribution is of hard X-rays. It was put together by Norma Crosby in 1993 from the, I think, OSO5 Higgs-Cerebus data, SMM Higgs-Cerebus data, if I've got that right. And you can see that it's a beautiful power law, except at the bottom, where there's obviously, bias against seeing small events because there's noise. And at the top, there's an intriguing, but not very clearly defined deficit. Okay, and so where's the Carrington flare in that? We would like to know. Just to comment about power laws generally, such things very commonly describe the occurrence distributions of a huge variety of natural phenomena. And earthquakes are a famous example. There's the Richter scale. The floods of the Nile River, it turns out, follow a power law in magnitude. The populations of cities, London is the biggest city, but then logarithmically, what is the second biggest city in the UK? I guess I don't know. Is it Birmingham? But the city magnitude, city populations actually turn out to follow a power law very closely. And if you count the frequency of occurrence of words in a given book, such as the Bible, this was done frequently, you find that the word distributions are also a power law, the Pareto distribution. So anyway, so we know what this power law is. And so based upon that, one can easily estimate the probability of any kind of bigger event. And that's been done by not very accurately, because as you saw, the statistics are very poor at the high end of this distribution. And there's a good paper by Jeffrey Love in 2012 that does this. And many people have done similar estimates, and they all get about the same answer. But is that the whole story? No, the power law is there, but there could be something else. And the something else idea has been called a dragon king, this exotic name. And I have a slide at the very end. If I have time to get to it, I will explain how that might work in reality, but just take it for granted that there could be a dragon king lurking somewhere in this dimly lit corner. And the dimly lit corner is down here, where it's dimly lit because we don't have very many events. The Carrington event would be somewhere in the vicinity of this red question mark at the energy that we just estimated. But a dragon king could be anywhere it wants to be, because the whole idea of the dragon king is that it doesn't obey, it isn't the same physics, right? It's something different. And so it could occur wherever it wants to. And so in principle, it could also occur way out here with huge energy. So we have to always understand that this power law distribution is quite beautiful, and it describes flares in the narrow sense that we understand them, but we don't really know enough about solar magnetism to know whether or not there's something else that might be going on. And this, in fact, of course, goes back to dynamo, the solar dynamo. And although I'm not an expert on dynamo theory, I'm pretty sure that there are still gaps in our knowledge that keep us from predicting, for instance, the distribution of sunspots on the solar surface, or even the 11-year cycle, much less this kind of plasma physics activity that we see in the form of these magnetic explosions. Right. So the initial conclusion of what I'm talking about today is that we can define a Carrington event as a flare, some combination of flare CME magnetic storm, which is at the top of the scale. The Carrington event itself was not superlative. It wasn't outside the scale. And so a similar one would probably not be disastrous. Okay, and the comparison, I'll make a comparison about how big a disaster it could be. But of course, there could always be a dragon king, right? And so how do we know? one way we would know is to do theory, but the theory, I think the simplicity of this cartoon here from a paper by Olanier et al. Tells you how poor the theory is, although Olanier probably would disagree with that. The state of the art is very low. And basically, this paper says, based upon the area of sunspots observed on the sun, one can scale to flare energy. So give me a big enough sunspot and I will give you a super flare. But this is based upon a fallacious correlation. People make a correlation between sunspot area and flare magnitude. And there's a fundamental error in how they describe this relationship, which is one thing. But the other thing, of course, is that a sunspot and a flare have nothing to do with one another. They're only very indirectly related in the sense that they're both magnetic. But a sunspot is a gigantic pimple on the photosphere, and a flare is this huge plasma physics energy release in the corona. And so there's no reason at all for them to scale together, except very indirectly. And that's what we know to be the case. So the theory, and there was another early paper by Shibata-san on dynamo limitations. So these theories trying to understand events as large as the Carrington event and their occurrence patterns and predicting them, much less Dragon Kings, are not likely to be very helpful. Okay, but empirically, observationally, we've got these new directions we can go in, thanks to partly this graduate student in 2012, Fusami Miyake, who was studying tree rings, carbon-14 in tree rings in cedar trees in Japan. And here's a cedar tree in back of her. And she discovered this amazing event in about 775 AD. And so there was a paper in Nature. Oh, not bad for a graduate student. But then she discovered another one. So in I think 996 AD, something like that. And so there was another paper in Nature. So this was a great achievement for a young graduate student. And then a third one was found. And these events are, if you understand properly, the carbon-14 is an isotope. So before I describe this in more detail, let's say the other new channel that we've got for trying to infer things about solar flare distributions above the super flare range is the Kepler stellar photometry, and I'll come back to that. So meanwhile, about the tree rings, this is great. Here's the actual time series in years. Here's 15 years. And you can see the histogram of annual samples that she did for the tree rings in this Japanese cedar tree. And there's quite a bit of debate about what could this be, this transient event. And it settled down to being solar in origin, partly because not just in her cedar tree, but also in oak trees from Europe and in kauri trees from New Zealand and from trees all over the world. In fact, one could get a very similar kind of histogram if one did annual sampling of the carbon-14. So why is carbon-14 interesting? I think you're probably all familiar with dating. This carbon-14 lets you date because it's an isotope that is not stable, and so its presence and its half-life allow you to do that dating. And the innovation that Miyake was able to do was to get higher resolution, or time resolution, where higher resolution meant not 10-year samples, but a 1-year sample. so technology, and this is not an easy thing to do. Nor is it cheap, apparently. So people have been scrounging around doing more of this, but it looks like only 3 events during the Holocene. Only 3 events. That's the number you should remember. And Holocene is about 10,000 years since the last ice age. The other thing you should remember about this is the time scale here. So you can see that these are annual samples. And so there is the danger that you may not have a single solar flare, but multiple ones. And that's almost never mentioned in the descriptions of these events. These distributions of radioisotope signatures reflect the fluences of solar energetic particles, SEPs, and they also follow power laws. This is a power law here, and there's a power law here. For SEP fluences above 30 MeV and above 200 MeV, and you can see it's in units of, I'm not sure what the units are actually, but you can see the distribution functions generally have this power law low energy or low magnitude range, and then the speculative, but somewhat backed up by the observational data, including data from lunar rocks, particle tracks in lunar rocks, and even on the Earth, radioisotopes integrated over decadal timescales. It looks like there's a break in this distribution. It looks like it's a power law initially, then it rolls over. And if you go back and look at this Crosby distribution, there is a paucity, a lack of the biggest events here. Now, the first thing you would do if you saw that lack of the biggest events there, would you say, is that because they're too big to see? Are they swamping your detector? Is there a systematic error? Or in fact, are there systematic errors? You do see the events, but you're misunderstanding their magnitude. So this kind of a deficit here really has to be probed carefully from the instrumentation point of view before you're sure that it's real. But anyway, here's a hint that a distribution does roll over, and there is, of course, a closer relationship between SEPs and solar flares than there is between solar flares and sunspots, for example. So it's quite possible, and Richard Lingenfelter first suggested this, that these distributions are in fact matching the flare energy distributions. And so it may be possible for this lunar record, for example, or the tree ring record, to give us a guide on how the biggest, how true solar superflares might have happened. And also I will modestly point out that this power law that we observe certainly here, but also in the flare distributions, is so flat that if you integrate it, it goes to infinity. And so flare energy is not going to be infinite. It's going to be limited by something, and that something will cause a break to occur somewhere. So we're still seeking that break. We're still trying to establish that it happens, but this is one way to proceed. Another way to proceed is through Kepler data. Now this is really quite nice. There's Kepler, but now there's also TESS, and there's going to be a European photometry mission coming up, whose name I'm forgetting right now. But in any case, you can do very precise stellar photometry from space because you don't have the atmosphere to look through. And so looking at solar type, quote unquote, solar type stars, Maehara, student of Shibata's, found many flares on solar type stars, so-called solar type stars. And here's an example of a light curve from this star, KIC 6034120. KIC stands for Kepler catalog somehow, initial catalog maybe. And you can see this star is doing a very regular, almost sinusoidal variation. And superposed on that variation, there are these peaks. There are maybe a dozen, or maybe 15 or 20 in this time series that you can easily see. And this time series lasts for 40 days. And this big event here is blown up here. The sampling, unfortunately, does not have very high time resolution. TESS is much better. But anyway, this is what a solar flare would look like at this kind of time resolution. This is fractions of a day. And the magnitude is colossal. But so is the magnitude of the sinusoidal variation. So if we look at the sun instead, so Kepler is looking at broadband optical light, kind of like the stellar of V magnitude, gathering as much light as possible, because the whole purpose of Kepler was to search for exoplanets transiting stars. So the higher the photon throughput, the better. So very broad band. And in the case of the sun, we have the total solar irradiance, which is in principle infinitely broadband. It's the bolometric measurement of all of the radiation from the sun, which you can do from space, where there is no extinction. And so these observations began in 1980. In this paper in 1981, Wilson et al. Showed that there are dips caused by sunspots crossing the solar surface. It makes sense. So this is, again, a many-day time scale. This is 150 days, almost half a year of variation. And here you see a dip, another dip, and a third dip. And you see fluctuations in the background here, which are kind of chaotic and irregular. Right? And we now know that a lot of this irregularity is due to, and a lot of the emission is due to faculae. So sunspots and faculae dominate the total solar irradiance, which would be the analog of the Kepler broadband measurement of stellar magnitude, the solar analog. And so, it's interesting because the sun, you don't see flares, but you do see dips. And the stars, you don't see dips, but you do see flares. So it's different. And so I'm calling this flariness and dippiness. And just to read this statement, the solar TSI exhibits low level, order 50 parts per million per 2-minute sample, fluctuations due to convection and P-mode oscillation, and pronounced dips due to one-off sunspot transits. This is dippiness. Flares only marginally exceed these fluctuations. There are only a handful of flares that might have been detected. One 5 sigma detection by the TIM instrument, which succeeded the original ACRIM instruments here. The Kepler time series for the most super flare stars do not show dips, but instead have persistent quasi-sinusoidal variability at large amplitude percents plus striking flare excesses. This is called flariness. It's generally known that across spectral stellar types, and looking at the variability of the chromospheric emission, for example, there are stars with chaotic variation, random noise-like variation, and there are stars that show simple oscillatory patterns. And so this distinction clearly is happening for what Maehara called solar type stars. And they're solar type in almost all respects, except for age. But in particular in surface gravity and surface temperature and rotation rates, they're a solar type, but they're not solar type in this key matter of magnetism because of these distinctions you can see. In fact, they're just totally opposite. One is flary, one kind of star is flary, and the solar type of star is dippy. And this shows the distribution of flare frequency versus period. And this is from a more recent paper, again, based upon the Kepler database by Notz et al., 2019. This is kind of, I think, the state of the art. And so let's look at this graph. It is, here's the rotational period of the star. And it's gotten, the rotational period, you understand, has gotten from the time series, except for long periods, right? From the time series, you can see rotational modulation. This is called gyrochronology. And you can do it for stars except for slow rotators, where it's hard to do because they're so slow. So, but in any case, we know how fast the sun is rotating. It's rotating at about 27 days period synodic. And so it turns out that the stellar flares in that period range don't exist. And so there are no statistics. And so this comparison of stellar flare occurrences somehow has come into a stellar physics problem, in the sense that the slower a star rotates, the less magnetism, and all of a sudden its activity switches from being flary to dippy. And the sun is in this dippy state over here. And so we cannot use these Kepler super flare stars as a guide, because the sun doesn't work that way. And just for reference, the Holocene here, this is about 10,000 years. This is the interval since the last ice age, 10 to the -4. flares per year. So we're just stuck. We don't have enough statistics of stellar flares, but it may be that the situation will change. These astronomical missions like Kepler and TESS are just huge data machines, and Gaia, for example. And so I'm sure that statistics will improve, and it will be very interesting to see the exact shape of this plot against the solar rotation parameter, perhaps other parameters that guide that we can use as proxies to identify something that we can apply to the sun in terms of prediction. That would be really good. Or we could see the Dragon Kings if they happen. Right. So what have we learned from these tree rings and Kepler events? First of all, the tree ring events appear to have had much greater SEP influences than even this quite famous solar flare of 1956. They're a little bit different. And so we have to be suspicious about their utility in terms of predicting solar superflares. The Kepler events also don't suggest a reasonable basis for extrapolation to the solar case. And furthermore, thinking twice about it, the meaning of event must be questioned, because in the case of the tree rings, one had to integrate it for 1 year to get enough signal to see the event. And so it's quite likely that more than one flare would happen in 1 year, since there is a high degree of coherence for solar activity, as the butterfly diagram shows you that coherence in space and in time. And so you have to think about compound events as a possibility. And one way around this, we're kind of at I think a standstill interpretatively here. One way around this would be to look for stellar CMEs to understand this tree ring link a little bit better. If we could see stellar CMEs, that would be great. Right, so this illustrates the compound event problem. This is Halloween, October 2003. All of a sudden on the sun, there were 3 gigantic active regions that appeared pretty much simultaneously in different hemispheres, in both hemispheres. And they all made X-class flares. And if you add up the sunspot areas, these 3 different regions, or the blue, the red, and the green here, add them up, you get this total sunspot area, which corresponded very nicely to a big dip. You can see the shape is actually correct, right? The shape here of this sunspot area time series, and this dip here that was presented in a nice paper by Ishik et al. 2020, which this paper incidentally was trying to describe this tendency for coherence in flare and magnetic field occurrence in terms of the nests of activity that Gazauskas and Kees-Zwaan introduced in the 1980s. So nests of activity, or I would like to think of it as broadband correlations between position and time, like as in helioseismology, the K-omega diagram. So in any case, one certainly could have multiple flares adding up to make one Carrington-like event, and it would be even more true then that no new physics would be needed. So how about detecting CMEs on stars? I just wanted to show you this because it's so nice. This is the Eve observation of a dimming event. This is how you detect CMEs on stars with sun as a star data. Eve measures the solar spectrum integrated over the whole disk in this wavelength range. And you can see this black line is the background spectrum that's coming from the sun. But if you subtract that from a flare time series, you can see 2 phases. You can see the flare excess, this is the red spectrum, or the dimming deficit, this is the blue spectrum. And you can see the different spectral lines are showing up. Here, these are hot lines, and here, these are not so hot lines, like iron 8, 9, 10, 11, and 12, and 13, the lines that are typically coronal temperatures as opposed to flare temperatures. So this is, if you could do this on the stars, that would be super duper. And I'll point out that this is a first paper on the Eve observations by Mason et al., but this is not our Helen Mason. This is a different Mason. This is a James Mason. Okay. And so let's do that. Let's somebody propose to do this, make an EV instrument that has large area. And to describe the glimmerings of success of such a mission, there's a nice paper by Baron et al. Just published in Nature Astronomy that shows some credible examples that hint at stellar dimming events. And so individual events may be detectable this way. Okay, so I'm coming to an end here, maybe a little bit too early, but I have at least this one slide that tries to say something concrete about dragon kings. Okay, so I mentioned that dragon kings are things which might be different physics. I think this is the idea. I don't really understand what this Sornet's ideas represent, although here's a nice Chinese character's description of dragon king. In this paper by Sornet, they ask, is there life beyond power laws? Well, yes, and it was known from the 19th century. This is a picture of a portrait of Poincaré, who invented the theory of dynamical systems, pretty much in the context of celestial mechanics, trying to calculate trajectories of oscillating systems. And if you have coupled oscillators can exhibit quite bizarre behavior. A single oscillator, like a clock pendulum, is very stable and just oscillates and decays, perhaps. And it makes, in a parameter space plot such as this, it would just make little loops that get smaller and smaller as friction overtakes it. But in the case of coupled oscillators, you can get very complicated patterns in the parameters. Two pendulums coupled by a spring is a very simple example. And such systems can exhibit chaotic behavior, in which case you have the probability density function for some parameter in such a system may look normally just to follow a power law, but then all of a sudden it goes crazy. That is unpredictable, and it has to do with how Poincaré's theory anticipated it to happen, and it can be very large. So you can see simple examples of this. I was at a colloquium where such an example was shown. The speaker had just this rotating thing that he rotated for a while, then all of a sudden it went crazy. So you can illustrate dragon kings very simply with Poincaré theory. And one final comment about the Carrington event as a threat to humanity, or an event of the Carrington class. No, not really. The Carrington event is quite famous because the telegraph wires smoked, and of course there's a lot of damage from events in this class that can happen to power grids and satellites. So I'm not belittling that, but you can sort of call it a few singed beards, because those telegraph operators in 1859 found their apparatus going up in smoke or something like that. But in the same century, there had been the Tambora volcanic eruption, about the same mass. The Carrington event involved 10 to the 17th grams. The Tambora eruption involved about 10 to the 17th grams. Of course, the difference is this is cold stuff in the stratosphere of the Earth, and that produced countless fatalities. Where this 10 to the 17th grams was ionized stuff out in the heliosphere, and although there's danger in these events, there's not catastrophic danger in the sense of mega deaths. So the conclusions are, I think I won't repeat these. No new physics needed, but the radioisotope records do hint at the possibility of a Dragon King risk. And I say this because of the particle spectrum inferred for the fluents. They have not just a carbon-14, but also beryllium-10 and chlorine-37. So one can estimate very crudely the particle spectrum. And these isotope events, these three events spread out in the Holocene, don't look like solar events, solar SEP events. They don't look like sums of SEP events. They look like something different. So there's a strong hint that there is something out there which is a Dragon King. So we must be very careful about, we must study these extreme events, and we must be very prudent about the risk. So thank you very much. I'll be happy to answer questions if there are any.